Hello. In this video, we will be finding the solution to the following problem. An airplane of mass m starts at a speed v0 in level flight. Lift equals weight, so no vertical motion. Its engine exerts a constant thrust T. The drag experienced by the aircraft is F sub d, which equals v times velocity squared. Find the speed of the airplane as a function of time. So let's start by drawing a free body diagram. I will draw the airplane as a rectangle of a mass m, with its center of mass being the origin. The thrust force will be pushing the airplane forward towards the right, and the drag force will be acting in the opposite direction of the airplane's velocity. As the problem stated, the airplane is in level flight, so its lift force and its weight, or the force on the airplane exerted by gravity, balance each other out. Now that we have our free body diagram, let's find out what the net force on the airplane is. The net force on the airplane is its thrust force minus the drag force. We can substitute the drag force with b times velocity squared. Intuitively, this drag force function makes sense, as the drag force on the airplane typically increases as the velocity increases, since the airplane is running into more air molecules and trying to push them out of the way faster. And b is just a coefficient to scale depending on all the properties of the plane and the air. So our goal is to try to find the velocity of this airplane as a function of time, given these two forces acting on the airplane. We can start with Newton's second law. Force equals mass times acceleration. In this problem, we are going to idealize the mass of the airplane as constant, with the mass loss from fuel use and other things as negligible. We know that acceleration is the time derivative of velocity. So if we arrange F equals ma to acceleration, or the derivative of velocity, to equal net force divided by mass, we have an equation that we can integrate and solve for the velocity of the airplane as a function of time. Acceleration equals dv over dt, which is force over mass. We found the net force of the object over here, so we can just plug that in. We can rearrange this equation with all the terms with velocity on one side and all the terms with time on the other side. We integrate this side from the initial velocity to current velocity, v, and integrate the other side from 0 to current time, t. You can solve this integral by hand or with an online tool like Wolfram Alpha, but in the end we get a solution of the following: square root of m times inverse hyperbolic tangent of the square root of b times v squared over t, all over the square root of b over t. And on the right side we would just get t. Plugging in the limits of v and v0, we get the following. The second term we can simplify down to just a constant c and move it to the other side. We can then just solve for velocity by multiplying the square root of b times t and dividing by square root of m, and undoing this inverse with a hyperbolic tangent and getting v by itself with more algebra. Square both sides and multiply by t, divide by b and square root both sides. Now we have velocity as a function of time. V of t equals hyperbolic tangent of t plus c times square root of b over t divided by square root of m. All of this multiplied by the square root of t over b. We can look at this function and visualize what a plot of velocity versus time looks like, and see it makes sense. The hyperbolic tangent function looks a little like this, where the velocity will approach an asymptote. And all of these other constants just alter and scale the function and where the asymptote is. This function makes sense, since as the velocity increases, the drag force on the airplane increases until the drag force equals the thrust force and there's no more acceleration or change in the airplane's velocity.